This is a short video about Group 1, the alkali metals. In this video we're going to go a little bit deeper and look at why the alkali metals have the properties that they do and what it's related to. To understand the properties of elements, we have to look at their electronic structure. So we need to have a look at the electronic structure of Group 1. What have they got in common? What is different? What is it like in the first place? So the three elements that you need to be aware of are the first three in that group. Starts with lithium, then sodium, then potassium. We write their electronic structures in a list of numbers. That number tells you how many is on the first shell, how many in the second shell, and so on. So lithium is in period 2. It has 2 electrons in its inner shell and then 1 in the outer shell. Sodium, 2 on the inner shell, 8 on the next shell, and 1 in the outer shell, and so on. You can see that each time you go down the group, you gain an extra shell, but the last shell always has only 1 electron in it. So there is a similarity between them and a difference. We're going to need those later. Let's look at the patterns of the chemical properties. Now we know from the previous slide that all elements in group 1 have 1 electron in the outer shell. When it forms an ion, that means that it loses that 1 electron and it ends up with a charge of +1. That happens to all of them. That affects how they all react and form compounds. So let's look at some examples, and here these 3, I have them reacting with chlorine, and in which case they react 1 lithium to 1 chlorine, 1 sodium to 1 chlorine. It's a ratio of 1 to 1. So you would expect, and it is the case, that rubidium and cesium would also react with 1 in a ratio of 1 to 1. When we look at oxygen, there is a ratio here of 2 lithiums to 1 oxygen, and you can see that this pattern is repeated, and you would know what to expect again for rubidium and cesium. And even if we look at something more complicated like a phosphate ion, we can see that there is a pattern in how they all react because of that 1 electron in the outer shell and it producing a charged ion with a charge of +1. That gives us similarities in the chemical properties. So we've looked at the similarities in the chemical properties. Let's look at the differences, and those differences are also explained by the electronic structures. And whilst we have 1 electron in the outer shell for each of the group 1 elements, that outer shell becomes a little bit further away because each one has 1 more shell than the one above it. That electron is further away. It means that it's easier for potassium to lose that electron. It requires less energy than for sodium, than for lithium. So if it's easier for potassium to lose that outer shell electron, that means that potassium is going to react more quickly. Now I've put the reasons why it's easier for potassium to lose that electron in grey because really we're starting to branch into really high level thinking. There is an electrostatic attraction between an electron, it's negative, and the nucleus, which is positive. The greater the distance, the smaller that electrostatic attraction will be. But more than that, because these things are very small, the electrons on these inner shells will shield this outer shell electron from the force of attraction from the nucleus. So the more electrons we have between the nucleus and the outer shell, the less strongly that outer shell electron is attracted. And what we will say, the scientific way of describing all of this, is that ionization energy decreases as you go down the group. The ionization energy is the energy you need to pull this electron away to make the potassium atom into a potassium ion. All of this then explains the reaction between the group 1 metals and water. They all react in the same way. They all produce hydrogen gas, which you can test with a lighted splint. They all produce a metal hydroxide, lithium hydroxide, sodium hydroxide, and so on, which you can test by adding universal indicator, and it will become purple or blue because it's an alkali. But how violently they react completely depends on what it is. Potassium reacts so violently that it will burst into flame. Sodium forms a really small ball that fizzes around, and lithium is less exciting because it doesn't react as much. It's more difficult for it to lose its outer shell electron. The ionisation energy is higher. This slide summarises all the key points that I've been trying to make. It shows how the equations for the reactions are all incredibly similar. The only difference is the element that's involved. The products have got the same style of formula. That's because all of these elements are in group 1. They all have one electron in the outer shell, meaning that when they form hydroxide, they form it in the same ratio, in the same way. The difference is in their reactivity. Because rubidium is the largest, it has the lowest ionisation energy and therefore reacts the quickest, so it's the most reactive. It loses its electron much more easily. You know this from school because we don't have any rubidium, because it would be too dangerous to add it to water in the classroom. Let me summarise the key points that you need to know from this lesson. You need to know what happens to the reactivity of the group 1 metals as you go down the group, just as a key fact, knowing that potassium is more reactive than sodium, that cesium is very reactive. You need to know about the similarities and differences between the electronic configurations. You need to know how many electrons do they have on the outer shell, and then what happens to the number of shells as you go down the group. Then you need to explain why they would have similar properties, using the idea of the electronic configuration. Well, what is the similarity in their electronic configuration that would mean that there are similarities in their chemical properties? And then thinking about their electronic configuration, why they would have different reactivities. What's different about the different elements? How are their electrons different? And that will tell you why their reactivities are also different.